Hi everyone, my name is Nick Geisa and I'm an application scientist at Asylum Research on Oxford Instruments Company. Today I'm going to talk to you about GetReal. GetReal allows you to calibrate the sensitivity and the spring constant of a cantilever without having to first touch it to a surface. Knowing both the spring constant and the cantilever sensitivity is vital for both quantitative force curve measurements and for knowing your true deflection and amplitude. AFMs measure the deflection of a tip by monitoring the position of a reflected laser spot on a segmented photodetector. Because of that, the actual measured quantity coming out of the AFM is a voltage which corresponds to the position of the laser and, by extension, the deflection of the cantilever. The thing is that for a lot of measurements we're interested in, having our data in terms of volts just really isn't enough. For imaging, for example, and especially for high-resolution imaging, we really need to know the deflection for contact mode or the amplitude for AC mode in terms of newtons or nanometers, not volts. And when it comes to force curve analysis, we usually use Hooke's law, which states that the force is equal to the extension of the spring in meters multiplied by the stiffness of the spring in newtons per meter. For both force measurements and for imaging, we really need to be able to convert this voltage that we've measured in the photodiode into something that's more meaningful to us. To get a measurement of our cantilever's deflection or amplitude in nanometers, we need to know the sensitivity of the cantilever. Sensitivity refers to the relationship between the volts that we measure when the laser spot moves on the detector to the true deflection of the lever in nanometers. We express this sensitivity as volts per nanometers. A lot of times we invert the sensitivity to make the units a little easier to work with. Also, because we're using an optical lever consisting of a laser, a cantilever, and a photodiode, we end up using the inverse optical lever sensitivity, or invols, to convert our photodetector voltage into real units. The most common way to calibrate the sensitivity of a cantilever is to perform a force curve on a hard surface. With a hard surface, we can assume that the sample doesn't deform as we press against it. Once we have that data, we can assume that the change in voltage measured by the photodetector is equal to the distance in nanometers that the Z piezo is pushed with, and that's how we get our sensitivity. The main drawback of this technique is that if we have a very sharp cantilever, it's usually damaged during that first force curve. Or if we have a cantilever that is chemically functionalized, we can actually damage or foul that chemical coating during that first force curve. Additionally, sometimes you might have a sample that does not have a stiff region where you can do your invols force curve, and this is very common with biological and polymer samples. The GetReal method we'll show you today is a great way of circumventing all of these issues. Before we move on, I'd like to tell you how you can access GetReal. Because GetReal is a new software feature, it's available via a free software update for all Asylum customers. You can get it on the Release Candidates section of the Support and Downloads page of the Asylum Research Forum, as shown here. You may want to pause this video here to copy the link. So, GetReal is going to use two methods to calibrate the spring constant and the sensitivity of the cantilever without having to perform that first force curve. Basically, this is an extension of a technique originally developed by researchers at Asylum, Trinity College, and the University of Melbourne, and it's referenced at the bottom of this slide. First, it's going to take a thermal of our cantilever to measure the Q and the resonance frequency. Once we have those two values, we can then use the Sater method to calculate the spring constant of the cantilever. After we get the spring constant, we'll use the thermal noise method to calculate the sensitivity, and this is a little different than how we usually use the thermal noise method. Normally, we'll take a known invols and then we measure the Q and the resonance frequency of the cantilever to calculate the unknown spring constant. With GetReal, we actually already know the spring constant, but we don't know the invols, so we just rearrange the thermal noise equation to solve for invols. All of this is under the hood. As a user, all that you need to do is to select the cantilever that you are using and then start the procedure. GetReal will do the rest. Okay, so now I'd like to show you a video of GetReal in action. So for this example, we're going to use an AC240TS on a Cypher AFM. I'm going to just close this PowerPoint presentation. Let's look up the AC240TS specs online. I'm going to go ahead and open Firefox. This is our web page. The specs are available in our probe store. So I'm going to go to probes and then probe store. And I'm going to say select probes, and the AC240TS is right here. When I click on it, I can see the list of specs. So Based on this information, I can expect to see a spring constant of somewhere between 0.5 and 4.4 newtons per meter. Average is about 2. And the frequency that I expect is approximately 70 kilohertz. And, you see usually that falls somewhere between 50 and 90 kilohertz. So now let's take a look at the software. What I've already done is I've loaded one of these AC240s into the Cypher AFM. I can see the AC240TS in the video window here, and I'll start by lining my laser up onto the cantilever using Spot On, right-clicking on the cantilever, puts the laser on there, then of course I have to zero my photodetector. I'll activate the software method by going to the Thermal tab and pressing the GetReal button. When I press that button, the cantilever panel comes up and I can see a selection of cantilevers that are available to use with the method. Since I'm using an AC240TS cantilever, I'll go ahead and select that from the list. I'll now start the procedure by pressing the GetReal button. As the procedure starts, I want to show you the Calibration tab of the force panel, and here we'll see that none of my calibration factors have been calibrated. That's indicated by the red dots on the left. As the procedure runs, you can see the thermal here in black, the blue line is the model fit, and the red is the bounds of the fit. And at the bottom left, you can see a status bar as the procedure goes forward. Once it's finished, you'll see that I have my results, which shows that my deflection in vols is 46.46 nanometers per volt, and my spring constant is 1.72 nanonewtons per nanometer, which is totally what I would expect for this cantilever. So now that I have both my sensitivity and my spring constant, I can start making some quantitative measurements with this cantilever. Using the sensitivity, I can convert my amplitude or my deflection into the real cantilever movement in nanometers. I can also convert my force curves into newtons for quantitative force measurements. So there you have it. I hope this video was useful to you. If you'd like more information, please do check out our user forum. There you can find many other short videos on various Asylum techniques. You can also find some videos that will expand on some of the topics mentioned in this one, such as spring constant calibration, AC mode imaging, and quantitative force measurements. And of course, as always, if you have any questions about this or about anything really related to your Asylum AFM, please do send us an email to support@asylumresearch.com, and we'll get back to you as soon as we can. Thanks a lot.